All right, it is a Venn diagram time. At the top of your notes, you can put 512 Venn diagrams. And then before we get there, I want to do a little blast from the past, remembering exponents, remembering scientific notation, because I'm going to throw it at you again a lot and without warning. And so I want you up on your game so you don't have to actually study for it when we hit the exam, because it's been sprinkled in. So try this. Simplify, no negative exponents, and divide, no calculator. Are you kidding me? Try those two. Pause me until you get it. Go. All right, so here we go. If you're simplifying this with no exponents, you can put the y's together. So put those and those together. So put the 2 out front. So this should be 2y. There's y times another y, so y cubed. And x cubed is still here. And all of this is still here as well. Fine. This negative brings all of this stuff up to the numerator. So you could think about it like 2y cubed x cubed times negative x to the fourth, right? This is negative x times itself 4 times, right? 4 negatives. Negative times negative gives you a positive. Negative times negative gives you a positive. Positive times positive. This whole thing is going to be positive, right? Regardless of what the x is. So essentially, this doesn't matter anymore, right? And really, you can think about this piece as just x to the fourth. A positive x to the fourth. So now we've got 3 sets of y's, 3 more x's and 4 x's, so x to the 7th. Cool? Bing! Great. With this mess, we're trying to divide, and what's nice about scientific notation is you can divide this part and divide that part and multiply them. So this should turn into 3/6 times 10 to the negative 2 over 10 to the third. This part's easy. It's half. And I'm going to turn it into a decimal in a second. We'll show you why. This, if you're not sure about it, think about maybe 2 to the 5th and 2 squared. Right? You'd have 5 2's up top and 2 in the bottom, and you'd cancel out these and cancel out these, and you'd be left with 2 cubed, which is 2 to the 5 minus 2, gives you that 2 to the third that you expect. You subtract this and this. So you're going to do the same thing here. Keep the base and say top exponent minus the bottom exponent. And that gives you half. Actually, I'm gonna write that as 0.5 now. Times 10 to the negative 5, right? And that's close to scientific notation, except that isn't in scientific notation. So I'm just going to turn this piece, instead of calling it 0.5, I'm going to call it 5 times 10 to the negative 1. And this is still there, times 10 to the negative 5. And then we can combine these pieces and call it 5 times, well, when you multiply powers, you add same bases, you add their exponents, so 10 to the negative 6. Cool, and so that's where you get this from. Bing! Blast from the past, should have stayed there. When you walk out of here, I want you to be able to solve basic probability problems with Venn diagrams. In the end, we're going to find numbers and not really probability. That's the next set. I want you to understand union and intersection. Cool. So let's try it out. Put this in your notes. Venn diagrams are a way to represent probabilities and sample space. So, for example, we want to find the probability of rolling. We're rolling a die, and we want the probability of getting less than 3. This is a sample space diagram that you and I know and love called a Venn diagram, right? Everything that could happen in the sample space is in there. You could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Everything's sitting there, right? We're calling event A, a number less than 3, right? Is 3 less than 3? No. If you were like, I want my homework to be less than 3 hours, and you got 3 hours of homework, you'd be mad, right? 3 is not less than 3. On our quiz, it was, I don't know, is 15 greater than 15? No, it's not greater than 15. It is 15. It's not bigger than itself. I can't answer those sort of questions for you then, but I can now. No, 15 is not greater than 15. 3 is not greater than 3. So, sorry, tangent, I'm trying to control myself. So we want all the numbers that are less than 3 in this circle of probability A. Probability A means it's less than 3. 1 and 2 are in there because they're less than 3, but none of these are. They're still inside the box, they're in the big square, because they are things that could happen. They're part of the sample space. Everything that's A is in there. Everything that's not A, this is A prime. We say A prime. That's this little guy. And that means not A. Yeah? So 3, 4, 5, and 6 are not less than 3. Cool? So these are all the numbers that are in the box, and 1 and 2 are in our sample space. So you could say, hey, look, I have 2 entries. I have 2 in A. The number of entries in A is 2 out of the number of entries in all of the sample space U. I sort of think about the universe, right? So here's the number of entries in the sample space. 1, 2, 3, 4, 5, 6. These 2 are still in the box, so they get counted in this piece, right? So 2 out of 6, 1 out of 3 is a way to find the probability that way from the Venn diagram. And I know what you're thinking. I know you're thinking a Venn diagram should look like 2 circles overlapping, and this is only 1 circle overlapping, right? So I know that you're used to seeing this as 2 circles overlapping. Bruce Lee, John Wayne, Bruce Wayne, right? And so this, maybe it doesn't look like a Venn diagram to you and you're freaking out, right? There's supposed to be 2 circles. Yeah, we're getting there, right? Calm down, nerd. We're getting there. We got to start with 1 circle, still a Venn diagram. But talking about sample space, we'll eventually get to 2 circles. So hang on. Okay, get your hat out of the way, G. So walk with me through this one. Venn diagram talks about sample space with children, students in a class, and event E is blue eyes. So you could think about E is blue eyes. Blue eyes. Great. So here's all the people in the class. Get your head out of the way, G. There's all the people in the class. 8 have blue eyes, yeah? Out of how many? Well, there's 8 that have blue eyes. There's 15 that don't have blue eyes. In total, there's 23, right? You added this and this. Now, we could have written their names like these. We listed all the entries. So we could put everybody's name in here. And we could say, okay, well, Mr. G has blue eyes, and I don't know, Mr. Tousley has brown eyes, and we could list all of their names and make dots for them or something. But a faster way to do it is just write the number that are in there instead of writing everybody's name and tallying them up. Just say, hey, look, 8 people with blue eyes, 15 with not blue eyes. In total, there's 23 in here. that make sense where this comes from? So what's the probability that somebody is just randomly selected and has blue eyes? Well, it would be 8 out of 23, this many out of the total. Fine. So what's the probability that you pick somebody and they don't have blue eyes? Well, it's this 15. These are the ones that don't have blue eyes out of the total. So it's 15 over everybody, right? That's one way to do it. Another way to do it is say 1 minus the blue eyes. I know 100% of the people minus the probability that they have blue eyes. So 1 minus 8 out of 23. That's another way to get you there. Okay. Disjoint sets. I'd like you to write this in your notes and draw this diagram. Notice no overlap. Cool, disjoint sets. All right, so disjoint sets are sets that where you have two things that aren't going to overlap. Like if you were flipping a coin, right? Sometimes you get heads, sometimes you get tails, but you never get an overlap. You never get like tails or heads, right? There's no overlap. They're disjoints. They're mutually exclusive. When one happens, the other doesn't happen. It can't happen. Like heads or tails. Here's another one that I like. These are the guys who want to date me, and these are the guys that I want to date. Maybe not me, but maybe. And they're mutually exclusive. They're not overlapping. They're disjoint, right? They're spread. So the opposite of that is a non-disjoint set. So a non-disjoint set just means it's a Venn diagram like we're used to seeing. Non-disjoint means there's overlap here, and there's some that can be in both A and B. Okay, so two pieces that I want us to be comfortable with are intersection and union. And so you should write this piece down and sketch this, and write this piece down and sketch this. And there's a word associated with both of them. All right, so the intersection is both have to happen. I need B to happen and A to happen. The key word there is and. So, for example, if we were rolling a die and A was even and B was prime. Prime numbers are 1, 2, 3, and 5. They're numbers that are just divisible by themselves and 1. Right? That's what's in B. The even numbers are 2, 4, and 6. So if this was rolling a die and this A was evens and B was primes, well, 1 and 3 and 5 are in there, and 4 and 6 are in there, and 2 is both prime and even. So it goes in the intersection because it's part of this circle and it's part of this circle. You don't write it in twice because that's redundant. Right? So there you go. That's evens and primes and, right? 2 is both even and prime. Right? The union is both of the things. It's this or that. It's like saying roll a die, and if you get an even or a prime, no homework for the rest of your life. Well, 1 and 3 and 5 and 2 and 4 and 6, all of those are good for you because they're either even or they're prime. Both is fine too. Cool. This is my favorite example. This is a I love how much time people have on their hands. This is a beaver with a flat tail playing a guitar, and this is a duck with a bill playing a keyboard, and this is a duck-billed platypus. He has the duck bill and the beaver tail playing a hybrid piano guitar. I love it. I didn't draw it. I'm not that creative. All right, so let's try this one out. Same sort of idea. Here's the people that play soccer. Here's the people that play tennis. I'd like you to pause me and think about, figure who plays both, and draw me a Venn diagram to show that. Well, it looks like Casey is in both, provided it's the same Casey, and Drew is in both. So if you drew this, this is the intersection. We want people who do both, who do tennis and soccer. It's these people, right? If you were doing either one, like, hey, if you're in soccer or tennis, you don't have to do homework tonight because I know you have a game or something. If the people that play tennis don't have to do homework, the people that play soccer don't have to do homework, and the people that play both definitely don't have to do homework. So this is the OR set. This is the union. This is the intersection. This is the and. I need both things to happen. Cool? All right. So, I like that one. You might have to pause me and piece that together on your own. Here, check that out. All right. All right. So let's try this out by just shading on our own. On a separate Venn diagrams, separate Venn diagrams means start with this for both of them. Here's, call that A, call that B. Here's the universe U. I want you to shade the region that's A but not B. Try that. And then for here, try to shade the region that is neither A nor B. All right, so A but not B looks like that. This intersection is not part of it because the stuff in the intersection is partially A. For this, the stuff in here and the stuff that's both of them is A or B. We can't have any of that, so it has to be shaded the outside region, all of this stuff, right? Great. Okay. So let's try this out with an example. So here's a sporting club. We have tennis, we have hockey, and we want to find just the number of people that have this and that. Okay, great. What I think is hardest to visualize about it is it's obvious that there's 27 people that play both. We are mathematicians and we don't like redundancy. We don't like saying the same thing over and over. It's really annoying to say the same thing over and over, and so we don't like saying they're counting the same number again. See what I mean? So there's nobody that's been counted twice here. So there are 27 people that play both. There are 26 people that only play hockey. They're right here. So how many people in total that play hockey? Well, if you think about it, I guess so we're doing B, right? If you think about it, these people, some play only hockey, some play both. So in total, 53. If you add them up, there's 53 in this circle, right? Same with tennis. Same idea with tennis. These are the tennis players, 27 and 15. So if you add them up, you find everybody who plays tennis. Okay, that's kind of hard to visualize. So how many people in the club? Well, 15 and 27 and 26. And these 7 people that don't play either one, right? Maybe they swim, maybe they play badminton, maybe they at a fence. But either way, add them all up. Bing, 75. Okay. How we did hockey. How many people that play both sports? Well, that one you're just reading right off the graph. 27. All right. Who play neither sport? Also reading it off the graph. 7. It's these people. Another way. Okay. Yeah. And those who play at least one of the 2 sports, right? Anybody who is a tennis player or a hockey player, no homework for you. Great, no homework for those people. They play hockey. No homework for those people. They play tennis. No homework for them. They play both, right? They play one or the other. So one way to do it is say 15 plus 27 plus 20 plus 26 is the number of people that play at least one. Right? Another way to do it, I think that's what 68. Another way to do it is say the total 75 minus the people that play neither of the sports, right? The 7. And you're still back to 68. Doesn't matter how you do it. Sometimes we don't have enough information to do this, so we can play this trick, total minus the one we don't want. All right, let's check. Let's check. Yeah. Cool. So your home learning looks like this. Actually, it looks like this. Venn diagrams. Boom. No, same thing. It's the one with the Venn diagrams in it. That one. Thinking, bing. Shade these. These are all numerical, right? Do both sides. There's the answers. Don't look at them ahead of time. Try both sides. You might get done. If you go on, which you're welcome to, this part actually starts taking into account the probability. But the hardest piece is building this inside. There should be a video up about this second part, Venn diagram probability, and you can check that out too and go ahead into that. Great.